Section 1. Introduction. In the previous video we answered the question, when is a triangular number also a square? That is, we solved the equation y squared equals x plus 1 over 2 for positive integers x and y. Our solution went as follows. Use the fundamental lemma to split this into two cases. One where x is a square and x plus 1 is 2 times a square, and another the other way around. And then in each case, eliminate x to get a relationship between the two squares. This relationship in both cases was exactly Pell's equation, which we have previously learned how to solve. In this video, let's look at a more interesting problem. A tetrahedron is a pyramid with a triangular base, a regular four-sided pyramid. Tetrahedra happen to be the most efficient way of stacking spherical objects. You may have seen oranges for sale stacked in a tetrahedron. That is, the top layer is a single orange, the second layer is a triangle of side length 2, the third layer is a triangle of side length 3, and so on. So this gives us the sequence of tetrahedral numbers, 1, 4, 10, 20, 35, and so on, where we get from one tetrahedral number to the next by adding on the next triangle number. So starting at 1, we add 3, then 6, then 10, then 15. Now we know the formula for the triangle numbers is n plus 1 over 2, so we can sum those to find that the nth tetrahedral number is n times n plus 1 times n plus 2 all over 6. Alternatively, now that I've given you the formula, you can prove it by induction. This video, let's ask, when is a tetrahedral number also a square? That is, when is the number of oranges in a tetrahedral stack, of side length x, let's say, equal to the number of oranges in a square tray of side length y? Well, let's write out a few values. We can see two solutions already. The number of oranges is 1 when x is 1 and y is 1, and the number of oranges is 4 when x is 2 and y is 2. Are there any more solutions? This video will argue entirely from the fundamental lemma, but in a short upcoming bonus video, we'll see that it gives us our first reason to be interested in elliptic curves. So let's get started. Section 2. The fundamental lemma. The equation we want to solve is y squared equals x times x plus 1 times x plus 2 all over 6 for positive integers x and y. Let's immediately multiply through by 6. Remember the slightly upgraded version of the fundamental lemma from the previous video. I'll state it with an extra variable this time. If y squared equals a times b times c, where a, b and c are all positive integers and their greatest common divisors are all equal to 1, then they must be squares. A equals alpha squared, b equals beta squared, c equals gamma squared, for integers alpha, beta and gamma, which we can take to be positive as well. But if there's an extra factor of 2 on the left, then there must be an extra factor of 2 on the right somewhere. And if there's an extra factor of 3 on the left, then there must be an extra factor of 3 on the right somewhere. Like last time, we're going to have to split our problem into cases. Now, I'm not going to cover all of these cases because there's a lot of repetition in the methods, but I'll cover a few to show the main approaches. Before we can even use the fundamental lemma, though, we need to check whether the greatest common divisors of x, x plus 1 and x plus 2 are all equal to 1. So, just like last video, if p divides x and x plus 1, then it must divide their difference, which is 1. So the greatest common divisor of x and x plus 1 is 1. Likewise, the greatest common divisor of x plus 1 and x plus 2 is 1. And the same argument shows that the greatest common divisor of x and x plus 2 must divide 2. In other words, it's either 1 or 2. So from here, our solution splits into two branches. If x is odd, then 2 isn't a divisor of x, right? So all the greatest common divisors are 1, and we can apply the fundamental lemma immediately to y squared equals x, x plus 1, x plus 2 over 6. Now if x is even, then so is x plus 2, so their greatest common divisor must be 2. Let's write x equals 2 times t. Then, substituting that into our equation, we get y squared equals 2/3 t plus 1, 2t plus 1. Now, as there's an extra factor of 2 on the numerator here, y squared must also be even, which means that y is even. So let's write y equals 2 times u. Finally, we get rid of the unwanted factors of 2, and we simplify to u squared equals t plus 1, 2t plus 1 over 6. This looks very similar to our original equation. T and u are still both positive integers, but now you can check that the factors on the right-hand side definitely have greatest common divisor equal to 1. So in the case when x is even, we apply the fundamental lemma to this set of equations. Let's now study some individual cases. Section 3. An easy contradiction. In this case, we're going to assume that 2 divides x plus 1, so x is odd, and we're going to assume that x is divisible by 3. Now we can apply the fundamental lemma to this immediately. We get x is 3 alpha squared, x plus 1 is 2 beta squared, and x plus 2 is gamma squared. These are 3 simultaneous equations. Just like last video, let's eliminate x. Substituting the first equation into the second, we get 3 alpha squared plus 1 equals 2 beta squared. Now, one very useful tool in solving integer equations is modular arithmetic. We've seen examples of this before. It usually won't solve the equation for you, but considering your equation modulo m for some value of m will allow you to uncover constraints on your set of possible solutions. We can then often use these constraints to narrow the solution set down. So if alpha and beta satisfy this equation, then they must satisfy it modulo m for any choice of m. And if we choose m equals 3, then this first term is always 0, so we effectively eliminate alpha from the equation. Mod 3, our equation reads 2 beta squared equals 1. But we've already seen, just by listing the possible squares mod 3, that this can't happen. The only possible squares mod 3 are 0 and 1, so the only possible values mod 3 for 2 beta squared are 0 and 2. So 2 beta squared can never equal 1 mod 3, and so we never get a solution to these simultaneous equations. And this is our method in a nutshell. We write down these simultaneous equations, eliminate x, and use whatever tools we have, which are often just modular arithmetic, to constrain the solution set. Unfortunately, there are many ways of eliminating x from these equations, and they're not all equally good. Sometimes eliminating x will leave you with an equation you don't know how to solve. Sometimes eliminating x will give you a partial constraint on your solution set, but still not narrow it down fully. These are genuine difficulties, and most problems like this do remain unsolved. Let's move on to another case. Section 4. Repeated application of the fundamental lemma. In this case, we're going to assume that 2 divides x plus 1, so x is odd again, and that 3 divides x plus 2 this time. Applying the fundamental lemma gives x is alpha squared, x plus 1 is 2 beta squared, and x plus 2 is 3 gamma squared. Now let's try eliminating x. There are 3 obvious ways we could do it. We could substitute equation 1 into equation 2, or into equation 3, or we could substitute equation 2 into equation 3. Here they all are. Now in this case we don't get an easy contradiction. There's nothing wrong with these equations individually, they do all have solutions. But the real question is whether they have simultaneous solutions. Are there values of alpha, beta, and gamma such that all 3 equations are satisfied at the same time? To answer this question, we need to know the relationship between alpha, beta, and gamma all at once. So let's try combining these equations, for example by adding multiples of them to each other to end up with a new equation that relates all 3. Now there are lots of ways of doing this, and there's no particular way of finding a nice one other than using your own intuition. If you play around with it for long enough, you might stumble across the equation 3 gamma squared equals 4 beta squared minus alpha squared. Both sides are just equal to x plus 2. And you might notice that the right-hand side is a difference of 2 squares. If you factorize it, you get 2 beta minus alpha times 2 beta plus alpha. And these factors on the right also have greatest common divisor equal to 1. So we can apply the fundamental lemma again to this inequality. Here again we have 2 cases. Either 2 beta minus alpha is divisible by 3, or 2 beta plus alpha is divisible by 3. In each case, one factor is 3 times r squared for some integer r, the other factor is s squared for some integer s, and gamma equals r times s. I'll only do one case because the other case is identical. Let's write alpha and beta in terms of r and s, and now substitute these into our original expressions for x. So x equals alpha squared, and x plus 1 equals 2 beta squared. And now we can eliminate x again. After a bit of simplification, we get a quadratic equation in r squared. So now we can just write down the solutions using the quadratic formula. Okay, I'll just make a bit of room here. Now, r squared must be an integer, which means that this expression under the square root, 2s to the 4 minus 2, has to be a square, so that its square root is a whole number. A bit of clever factorization later, and this can be written as 16 times s squared plus 1 over 2 times s squared minus 1 over 4. These three factors can be shown to be integers, and again, they have greatest common divisors all equal to 1. So, one final application of the fundamental lemma tells us s squared minus 1 over 4 must be a square, so s squared minus 1 must be a square. In other words, we have two square numbers next to each other. But this only happens when s squared equals 1. So, finally, after these three applications of the fundamental lemma, we have a solution. But unfortunately, it's not an interesting one. Substituting it back up the chain of equations, ultimately we get x equals 1 and y equals 1, and we've already seen this one before. Now let's look at the more interesting case. Section 5. Pell's equation. In this case, I'm going to assume that x is divisible by both 2 and 3. Now, we saw before that this means the greatest common divisor of x and x plus 2 is 2. So we're going to have to divide out by all the common factors of 2 first. Setting x equals 2t and y equals 2u gives us the equation u squared equals t plus 1, 2t plus 1 over 6, as before. Now in this equation, t is still divisible by 3, and 2t plus 1 is always odd, so the factor of 2 must occur in either t or t plus 1. But if t is divisible by 3 and t plus 1 is divisible by 2, we get the same easy contradiction as in section 3. So t must be divisible by both 2 and 3. Okay. The fundamental lemma now gives us t equals 6 alpha squared, t plus 1 equals beta squared, and 2t plus 1 equals gamma squared, for integers alpha, beta, and gamma. As before, we start by finding a way to eliminate t. The obvious ways don't give us many interesting constraints. But we don't only have to add or subtract these equations from each other. We can also do more complex things to them, such as multiplying them together. For instance, multiplying the first equation by the third gives us 2t squared plus t equals 6 alpha squared gamma squared. If you were playing around with this, you might think to multiply it by 8, giving you 16t squared plus 8t on the left, and you might notice that this is almost a square. If I add 1 to it, I get 16t squared plus 8t plus 1, which is 4t plus 1 squared. That equals 48 alpha squared gamma squared plus 1. But now I can get beta involved. I can rewrite 4t plus 1 as 4 beta squared minus 3. What have we accomplished? Well, if we write capital A equals 4 beta squared minus 3 and capital B equals 4 alpha gamma, this equation tells us that a squared minus 3b squared equals 1. This is Pell's equation. Okay, we know how to solve Pell's equation by playing with continued fractions. We can find the fundamental unit 2 plus root 3 for z adjoint root 3. Then any solution is of the form a equals plus or minus pn and b equals plus or minus qn, where pn plus qn root 3 is the nth power of that fundamental unit, as n ranges over all possible integers. But since a and b are positive, we might as well restrict to plus signs here, and positive integers here. So, let's write out the first few values in a table. I'll omit the partial denominators this time because I've given them in previous videos, and I'll just give the convergence. Now, last video we had to solve Pell's equation, and that's all. Any solution to Pell's equation gave us a value of x that solved our problem. However, this time we're more restricted. Not only do we need a and b to be solutions to Pell's equation, a squared minus 3b squared equals 1, but we also need a to have the special form 4 beta squared minus 3. Just like our first example, that puts an extra constraint on our solution set. So which of these possibilities for Pn also fit the pattern 4 beta squared minus 3? Which of the numerators Pn are 3 less than an even square? Well, a quick look through the list and we find a potential solution given by a equals 97. And in fact, substituting that back up the chain, we get beta squared is 25, so t is 24, which gives us x is 48, y equals 140. Finally, we found a non-trivial solution. A stack of oranges of side length 48 contains as many as a square tray of side length 140, that is, 19,600 of them. Now, could there be more? These numbers get big very fast, so it's going to be hard to check them all unless there's some underlying pattern to them. Section 6. Congruences. The positive solutions a equals Pn, b equals Qn to the equation a squared minus 3b squared equals 1 are given by powers of the fundamental unit. Pn plus Qn root 3 equals 2 plus root 3 to the n. From here we can derive lots of easy congruences. For example, the m plus nth solution is Pn plus n plus Qn plus n root 3, that is 2 plus root 3 to the n plus n. But we could write this as the product of the mth solution and the nth solution, that is Pm plus Qm root 3 times Pn plus Qn root 3. Expanding this out, and equating the integer part and the root 3 part, gives us these two relations. A bit of repeated substitution later, we can derive the following congruences. Pn plus 2r is congruent to Pn mod Qr, and Pn plus 2r is congruent to minus Pn mod Pr. This is a kind of periodicity. For example, setting r equals 2, we can see that Pn is equal to Pn plus 4 mod Q2. Q2 is 4. And we can see that Pn is equal to minus Pn plus 4 mod P2. P2 is 7. So our convergence Pn and Qn contain a lot of regular repeating patterns, mod 4 and mod 7. And setting r equals different values will give us different congruences too. Okay, well, remember that what we wanted was to find values of Pn such that Pn was 3 less than a square. Well, for example, let's set n equals 2. Now, P2 fails this test. P2 is 7, which is not 3 less than a square. And using this periodicity, we can propagate this failure to be 3 less than a square to other values. So let's keep n equals 2 and set, for example, r equals 5. Then our first congruence tells us that P12 is P2 mod Q5. In other words, P12 is 7 mod 209. Now, 7 also isn't 3 less than a square mod 209. Nothing will square to 10 modulo 209. So P12 also fails our test for the same reason mod 209. But now we can repeat this process. If P12 fails, then so does P22, and so does P32 and P42, and so on. None of these can be solutions. I'll omit the tedious details, but checking a few more congruences like this will show that there are no more solutions, and we have now found them all. The papers containing them are normally very short, so I'll leave a small bibliography in the video description in case anyone wants to chase them up. Notice the important tool we used here, identifying squares modulo a prime. This isn't the first time we've used this tool. In video 2, we wanted to work out when a prime number p split in z adjoin I. Right. For odd primes, this turned out to be the same as asking when there was some Gaussian integer a plus bi with norm p. In other words, p could be written as the sum of two squares, a squared plus b squared. In video 5, we saw Euler's criterion, a test of whether or not -1 is a square mod p, and as long as p is odd, -1 is a square mod p if and only if p can be written as the sum of two squares. These topics are all very closely interlinked, and there's a lot more to say about them. We'll revisit them all very soon.